C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry-standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty, good day, folks. Thank you for joining today's webinar. We're going to get started here in a couple minutes. Just wanted to do a few housekeeping items before we officially begin. Today's session will be recorded and available for playback at the end of today's webinar. So if you have to maybe drop off earlier, if there are some colleagues of yours that may not have been able to make it, but you think this would be interesting for them, the recording will be available later on. I'll also make note of the Q&A feature. So during today's session, if you have any questions based on what was presented, maybe something related to work that you're doing, please feel free to type those questions into the chat box. We will be reserving some time at the end of the webinar today to go through those together. So with that, all that being said, I think we can go ahead and jump right in. So welcome again to today's webinar titled Material Characterization for Food Packaging and Cold Chain Storage. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And in today's session, I'll be joined by two of my colleagues, Arya Sharostambik and Alex Mann, to also discuss some of the aspects in this space related to DMA, as well as thermal analysis. So I'll be kicking us off here with, start with just a brief introduction to C-Therm. So for those of you who are new to these sessions or new to C-Therm, a little background, we are a Canadian-based company specializing in transient thermal conductivity measurements, really with the goal of simplifying thermal conductivity testing for the materials of tomorrow. Our core product is called Trident. So Trident, you can see here, this is a modular system for the measurement of thermal conductivity and related properties. There are 4 different methods available on this platform. Really, it comes down a lot to, the specific type of sample that you're working with, the conditions you're looking to test under. This can dictate which method is most appropriate, really taking the approach of a toolbox approach here, being able to pick and choose the best method for the task at hand. So of the 4 methods here today, a couple of these will be highlighted in today's session related to the application. And we'll provide some information on, the testing requirements, and then also some application data just to kind of, walk you through what that could look like for your research. And as kind of mentioned at the beginning there, I will be joined by my colleagues who will be discussing some other areas of characterization related to this space. C-Therm, we are partnered with and the distributors in North America for both Rigaku and Metrovib for their thermal analysis line and DMA product lines, respectively. I'll also mention we do have a full-service thermal analysis lab here at C-Therms. It's called Thermal Analysis Labs, TAL. So, if you were looking to maybe get some material testing done, you might not be ready to bring an instrument in-house, but you have some samples you're looking to get measured. Our contract testing services are also available for that. You'll probably see some messages showing up in the chat there as well. My colleague Emma, who's moderating today's session, will be dropping in some different references and links throughout today's presentation. So yes, if you'd like to learn more, as we're going through today's content, we are certainly happy to set up a technical consultation, maybe meet with you one-on-one, learn a little bit more about the specifics of what you're interested in pursuing. Certainly happy to help in that avenue. Also, if you're just looking maybe for some budgetary information, looking to get a quote for any of the instrumentation, again, certainly happy to accommodate that. You can find the links related to those posted in the chat here today. So before we go into the official session, we always like to kind of end off the intro with just a testimonial. We do have a variety of testimonials available on our website. Feel free to go check those out to see what folks are saying about their experiences with us and the instrumentation that we provide. This one here is from Nina Ravandi. She's a technical officer at the National Research Council of Canada. She comments, overall, I found the C-Therm's Trident thermal conductivity measurement system to be reliable and user-friendly. Its performance has been efficient in delivering accurate and consistent results. So always nice to hear what folks are saying about us. Again, follow the links there if you wanted to see what other folks are saying. All right. Now this brings us to, really the start of the official session here in terms of cold chain storage and food packaging. I'm going to kind of kick us off with some information related to the thermal conductivity side of things, looking at C-Therm's product line in this space. So what are cold chain applications? Again, kind of doing a little bit of a review here. Really what this comes down to is looking at, what systems exist, what, tools are out there to ensure that temperature sensitive materials, components, whatever those may be, can be transported and stored under the desired conditions. So whether this is like looking at materials that are harvested or manufactured all the way through that cycle to the point of use. A big thing that we'll be looking at here today is really the packaging materials that are involved. These are inherently designed for thermal stability. This is going to be a really important aspect of what we're describing here today. And specifically looking at, certain insulation materials as well, specifically from a thermal conductivity perspective in terms of maintaining that desired temperature, reducing temperature fluctuations and things of that sort. So what goes into a cold chain process? So, really it somewhat depends on the specific use case, of course, but generally speaking, these refrigerated or cooled storage devices or areas for equipment transport, packaging with insulation, there may be different PCMs, phase change materials, or active cooling introduced inside of these devices. There are certainly some, more on maybe some of the medical grade cold chain applications where there's active temperature monitoring. So, certain maybe, bio-based samples or vaccines, for example, may need to be very closely monitored in order to ensure that they are safely handled during transportation and things of that sort. Now, you can also look at this in terms of maybe more commercial type transport packaging. Have a picture here, an example of some of those meal prep boxes or like food transport that's occurring. Again, different components built into some of these systems. If you're maybe just the standard cardboard based box, so the actual cardboard itself can be an important material to characterize and optimize just as the overall enclosure. But then inside of that, of course, there could be different types of fibrous-based insulations, different metal-lined insulations, cold packs, the PCMs. Again, there's quite a variety of different materials that really go into these types of systems. And again, depending on the level of scrutiny that we're looking for, again, for maybe food-based transport versus something in the medical space, there can, of course, be different thresholds of what is required. But this brings us to, thermal conductivity and really its relevance here in this space. So I always like to just give a quick explanation of thermal conductivity. Again, some folks this may be very familiar to. For some, this might be brand new and you're just starting to get into this space. So thermal conductivity is effectively the ability of a material to conduct heat. So how well that sample or that material can transfer heat through the sample of interest. When we talk about thermal conductivity, this is an intrinsic property of the material. So essentially meaning it's independent of the size or the shape. In insulation in particular, some folks might be here kind of in that space. There's sometimes the term R value or thermal resistance that comes up. And thermal conductivity is a big part of that, but the big differentiator that I would say here is if you're looking at an R value or a thermal resistance value, it also takes into account the thickness of the material involved. So whether you're looking at just more of the pure material property measurement or that more object property with the actual thickness introduced, there can be a few different routes to look at this type of performance. So why is thermal conductivity important? Well, again, really here we're talking about temperature regulation, temperature stability in this application. And of course, for that, we have to understand the materials involved to help accommodate that ultimate goal of ensuring that, uniform, consistent performance. So other aspects like the energy efficiency, the shelf life of the materials involved that are being shipped and transported, the stability of the material, which will be discussed in terms of thermal conductivity, and also some of what Alex will likely be talking about with Rigaku's products. These all play an important role there in terms of optimizing and getting those systems to the point that they're efficient and of course going to be reliable for the application that they are used for. Now, this brings us to a point about why transient methods. So when we kind of look at the overall picture, thermal conductivity can be broken down primarily into transient and steady state methods. For us here at C-Therm, of course, we focus exclusively on the transient class of measurement. And there are a few benefits to transient that I'll kind of just point out here. One is the representative testing condition capabilities. Generally speaking, these systems, these methods can very easily be placed in different environments to mimic some application or application condition or represented environment of interest. So whether that's temperature, humidity, saturation, the compressibility of the sample, these are all variables we can play around with in conjunction with that thermal conductivity measurement. They're also much faster. So transient techniques, typically your measurement times and the analysis, it's seconds to minutes in duration. So a lot of folks in the, I'll say like R&D development space, this is a really nice way to do that assessment because it really helps to improve your throughput capabilities by giving you good, reliable data, but in a much faster way than, again, the more traditional steady state options. And the last one here is the inherent flexibility on the types of samples we can measure. So kind of just talking about that food packaging box, we had everything from like cardboard insulations to metals to PCMs. Oftentimes, these transient techniques, they're very flexible in the types of samples we can measure. Now, of course, certain methods are more appropriate than others in certain situations, but typically we do have options for measuring both solids, liquids, powders, pastes. Quite a diverse format of samples can be assessed. So this brings us to our first method that we're going to look at here, which is the MTPS. So this stands for the Modified Transient Plane Source. So this is C-Therm's proprietary sensor design. It's a single-sided interfacial sensor for the measurement of thermal conductivity and thermal effusivity. Really, one thing I just really want to point out about this sensor, this method, is the size. So the active area where the test is performed is across this colored region of the chip right here. And this measures about 18 millimeters in diameter. So in terms of just, what is the minimum that I need to be able to test on this device? If it's a solid, we need to at least cover that active zone. There is no maximum size limitation here. You can test larger pieces so long as we are covering the minimum area. That's really going to be criteria number one. So I want to share a couple different examples and use cases that the MTPS can really assist with in this space. There are quite a variety of applications for the MTPS. You can kind of see some of these on screen, but we're going to take a look here first at insulation as it really relates to some of the key components of these cold chain and packaging applications. When we're talking, I mentioned earlier about the representative testing conditions, especially with insulation, especially the non-rigid type. So any type of softer, more compressible, like bat form insulation. One of the really interesting things that we see groups looking at is the impact of compression. So if you are going to densify your sample, apply a certain force on the material, or maybe in application, it's compressed by a certain degree, this can impact the effective thermal conductivity based on the inherent changes in the density of that material. So as you decrease or push down on the sample, its thickness changes, but it's also increasing in density, which has a correlating effect of decreasing the thermal resistance. increasing conductivity and effusivity. So being able to control for one of the variables here, the compression of the sample, can be really useful in, again, getting really comparable data, especially if you're looking at trying to find, well, which is my best material to use in a given application? Well, we want to, one, test them in a similar way, but then also ideally represent the end use case. So we're really doing that apples to apples comparison. So with the MTPS, we do have a nice accessory, like off the shelf, ready to go for this type of testing. The compression test accessory, or CTA, you can see here. This is just one tool that can be added in conjunction with the MTPS to help accommodate that type of measurement. You can see here, this is basically, it's a force gauge that is allowing you to measure, as we lower this down into contact, how much force are we actually exerting on the sample. We can also measure the overall displacement here as well. But again, just a nice way to control that to make sure we get some good, reliable consistency in our measurements. And again, as I highlighted, the effective thermal conductivity can be impacted by that level of densification. So as we are increasing that compressive load on the sample, so kind of really, again, like squishing it down more and more, we can typically see a trend, something of this nature. So this was on like an insulation sample, where as we increased that force load more and more, we started to get a higher thermal conductivity. And again, for insulation, of course, we typically want to target a low thermal conductivity, which would correlate to, of course, a higher thermal resistance. But again, just understanding how that material will behave under those different states can be quite informative in determining what are your breakpoints in kind of the setup and the design of those systems. Wanted to share a publication here as well. So this is a group that was doing some work in 2017, but looking at bio-based insulations. Now, this was for a building material application, but I did just want to share the data because it was really interesting in that, one, they were looking at the thermal conductivity clusters based on the different samples. You know, bio-based materials were, of course, a little more variable in nature than the synthetic counterparts. But really the more interesting thing I wanted to highlight was the study they did with respect to cycling of relative humidity and the impact on the thermal conductivity performance. So with insulation, saturating or getting it wet, or putting it in a higher humidity environment is oftentimes quite detrimental to its insulative performance. Typically higher humidity, higher saturation will have a higher effective thermal conductivity than the lower end. So there are some materials that are more prone to this than others, but they did a really nice investigation here by cycling the humidity condition. They did quite a long measurement. This was a 30-day experiment looking at the cycling performance of some of their samples. But ultimately, just a really nice example of how folks are taking the methods here and looking at some of these peripheral variables like compression and humidity on how that impacts the overall performance of their materials. Oh, and this was a picture from the paper again here. They had a specialized glove box for their humidity environment. Again, one of the really nice things about these different transient-based sensors is that we can very easily put them in these different environments without risking damage to the sensor. So, in this setup here, they would have simply a little connector port that the sensor would feed in through. It would be sealed up so that the actual instrument is outside, but your sensor and your samples are placed in your environment of interest. So whether you're just looking to measure it out on the benchtop or take it a step further in some of these environments, certainly something you're capable of doing. Another one here, just wanted to share, this was from 2019, a group looking at PCMs, but specifically shape stabilized phase change materials. They noted again with an aspect of a high humidity environment consideration, but PCMs are oftentimes used in some of these cooling technologies, but some of the challenges is as they cycle, they lose their structural integrity during that liquid to solid phase transition and then back. So what some folks have been investigating is a way to essentially stabilize them using some type of scaffolding or secondary material to help improve on that aspect of things. And here, just kind of highlighting some of the results. So they were comparing their materials against a pure paraffin wax, different materials, different additives inside of their mixture. Again, kind of seeing the different trends, your highest performer versus the lowest performer. Depending, again, if you're looking to achieve a high or low thermal conductivity, you can use these types of measurements to, of course, baseline your performance and then see how your addition or modifications are getting you closer to that goal, or perhaps in some cases further away. But it's important to be able to actually be able to test for that, of course, right? So we can really get that direct measurement data to understand if we are going the right direction or not. So that was some little background on the MTPS. I do just want to share some examples with the more traditional transient plane source, or TPS, sometimes referred to as a hot disk style sensor. This is another contact-based sensor design, but this one's actually double-sided. So it has a little bit of a different setup, but it does offer some unique testing capabilities that, of course, differ from what we would have shown on the MTPS. One of the points I wanted to make here is that in cold chain storage, there is a variety of temperature conditions that may need to be met. Looking into it, many just simply require like a 2 to 8 degrees Celsius range. So kind of on the lower end, below your like room temperature, but not quite into that cryo point yet. But again, some of the more specialized devices in cold chain storage, for cell therapies, for example, are noted to require temperatures as low as minus 150 C. So again, taking your materials and testing them under that temperature point of interest can be quite important. And with the TPS method, we have done some testing down to lows about just shy of minus 200. Really in kind of like that liquid nitrogen environment. So here are some example data sets that were collected on kind of a stainless steel and also water. It would be ice, of course, at that point. But just seeing how that behaves based on certain theoretical assumptions going down that low. So with the TPS, you do have a nice option here to do direct measurements under cryogenic conditions. The other thing, and this is the last example I have here with for the thermal conductivity side, but is thin film. So some of these packaging materials, there may be different like barrier films or just, plastic films involved in the overall system design. But thin films testing is a little bit different than your more traditional bulk material measurements. One of the big challenges is with the thin film is related to the thickness, right? However, on the TPS, we do have a utility to directly measure your thin film materials, looking at samples down as low as about 10 microns in thickness. So again, just different methods, different benefits, and different kind of geared towards different functions. But with the TPS, a nice way to measure your thin film samples. So again, if any of this type of material was relevant to stuff that you folks are working on, would love to have a conversation about that and see if this would be a fit for your testing needs. This was just some example thermal conductivity of some reference thin film materials. So you can see some of those here that have been measured and characterized by our lab. So with that being said, that brings me to the end of my section. Again, if any of this was of interest, you wanted to learn more, certainly happy to accommodate that with a technical consultation, or of course, we can provide some budgetary information. Again, all these links have been posted in the chat, so definitely feel free to click on those if they are of interest to you. So I'll go ahead and stop sharing here and invite Alex to join us next to take us through his content. Thank you, everyone.
Thanks, Arya. Just give me one moment to set up here. So as previously mentioned, my name is Alex Mann. I'm a materials testing engineer in training at C-Therm. And I'm going to speak a little bit about Rigaku and the cold chain storage. So Rigaku is a company that is well known for their X-ray technologies, but they do also have a fairly robust thermal analysis line. So as you can see, it consists of our DSC, our Differential Scanning Calorimetry, our STA, our Simultaneous thermal analysis. This combines TGA, thermogravimetric, as well as the differential thermal analysis. And lastly, they have their TMA. So first off, what measures what? Starting off on the right, we have TMA. This is great for measuring expansion or shrinkage due to different temperature changes. So from this, we can measure glass transition, phase transitions if they're solid-solid, as well as expansion, shrinkage, sintering, even softening temperature. This is great for packaging materials to test their expansion, their shrinkage, or if they have a low or a high CTE, which can impact their, how stable they are at different temperatures, as well as softening. Then next, we'll move on to the STA. Not as popular in the food chain in cold. This is just because at normal, the STA is really built for high temperatures. And if we're using our cold chain storage, we're normally at lower temperatures. So the STA, in certain situations, it can do heat capacity, glass transition, Curie point. But what it excels at is, melting, crystallization, phase changes, as well as things where there's mass loss as well. So decomposition, dehydration, combustion, oxidation. And what we're going to be speaking about a little bit more in depth is the DSC, very accurate sensor. It can go very low, great thermal range. So it's good for heat capacity, melting, crystallization, glass transition, phase transitions, Curie point, oxidation. So how does that relate to food storage and cold chain? Well, we'll start off the glass transition, really important for determining, the glassy zone or the rubbery zone of polymer. So essentially, is it going to be brittle? Is it going to be rubbery and malleable? For example, when you squeeze a tube filled with, food or toothpaste, it doesn't crack or break. It bends. It's rubbery. Similarly, plastic bags, they're malleable and tear resistant. This is because the polymers used to make these things, they're above the glass transition. They're in the rubbery zone. Next, we have crystallinity. This is important because it gives an insight into transparency versus opacity, as well as flexibility and impact resistance. The fusion temperatures are also really important for determining the upper limits of the plastics or your insulation and whatnot. For example, you don't want to take stuff near the melting point because then it gets really soft, becomes a liquid, loses shape. Especially great, for example, if you're taking food and you store it somewhere, like a hot soup, you don't want to melt your container. And lastly, the specific heat capacity and the enthalpy of fusion are especially useful for thermal management, especially in the phase change materials, which Aria touched on a little bit. So starting off with some examples, some polymers are crystalline by nature, but we can force them to be amorphous. So what this means is that the polymer wants to have its molecules in a nice orderly crystalline fashion, but we can force them to be random or amorphous. So we do this by melting the crystalline polymer, and then we quickly reduce its heat. So we quench it, and by doing that, there's not enough time for the molecules to get into a nice ordered structure. They freeze in a random orientation. So however, when we heat this plastic back up, we give it some energy, it undergoes a cold crystallization where it can return back to its crystal state. So on DSC, what that looks like here, we'll take a look. First, I'll kind of explain what's going on. We took a PET bottle, just a typical bottle, juice, water, pop, and we looked at the top, the sides, and the bottom. Because when we quench it, it's possible that not every location receives the same cooling rate. So what we can see here is the top. We have a nice glass transition, which is shown by the shift in the baseline. Then we have an exothermic event, which happens immediately after. This is actually the the glass transition, followed by the cold crystallization, where our polymers go from amorphous or random, no specific orientation, back to a nice crystalline ordered structure. Then after that, we can see we have a nice sharp melt, which is a characteristic of a crystalline material. So this is the same for the bottom. So we can say the top and bottom are amorphous rich. In the middle here on the sides of the water bottle, we can see that there's no shift in the baseline, no glass transition, and then there's no crystallization event. But then we have it followed by a sharp melt. This means that this has no amorphous. It is a crystalline part of the bottle. So this is important for amorphousness and crystallinity because they affect properties such as the transparency, so you can see into the water bottle, as well as flexibility, so when you bend it, it doesn't snap, and it will impact resistance in case it's dropped or, it's a little banged up, etc. This was a study done on DSC. The researchers made rice pasta and then they exposed it to different levels of humidity for time. They then used DSC to determine the glass transition of the pasta. They then compared their data to a model called the Gordon and Taylor model, which looks at the pasta as a binary system of the dry solid and the water that it took from the ambient humidity. As we can see here, with an R squared of 0.964, it does fit the data fits the model prediction pretty well. We see we have the nice slightly curved line as the model prediction, and then the data points is what was sampled. So this is important because pasta needs to be stored below its glass transition temperature. So what we can get from this is the takeaway is that as we increase the humidity, the glass transition temperature decreases. So what that means is that as we get more humid, the temperature which we can safely store this pasta at decreases. So if we see here at around 20 degrees Celsius, which is about ambient, follow across, and the mass fraction of water in the pasta cannot be above 0.18, or it can't be more than 18% water by mass. So that's great for storage condition if you have it on the shelf at home, or if you're transporting it from the factory to the market. So next, I'm going to introduce some thermochromic compounds. A thermochromic material is a compound that changes color when it gets exposed to heat. So the following test was done using the Rigaku DSC, and it was equipped with a sample observation so that you can see what's going on during the entirety of the DSC. It helps you match your events with the sample's color change. So as we can see here, looking at our data, the thermochromic compound goes through a color change at around 60 degrees Celsius. So the ink changes from blue to transparent. And then on the cool down, we notice that as we go through 60, the ink remains transparent. So then lastly, once we cool it down to -40, the blue pigment in the ink is regenerated. So what we see here is that this thermochromic compound is reversible. However, the regeneration temperature is way below the initial color change. So in terms of food storage, how is this useful? Well, this is really useful for safety labels. If the temperature drops below 0, the formation of ice crystals can damage the food, ruining the texture and the flavor. So there exist these cold indicating safety labels. So these are irreversible, meaning that even if the sticker briefly reaches the set temperature, the color change will be permanent. Now, some of them are regenerable, as we mentioned, but as you see, the temperature which this occurs at is way, way below ambient conditions, which you need special equipment to reach. So that prevents any tampering. And on the opposite end, high temperatures can lead to premature food spoiling. So this label is an irreversible heat indicating label. And it shows the maximum temperature that this box or the sticker or the package has reached during its transportation. So if someone receives this and they take a look at the safety label and they see the colors changed, it kind of gives an indication to them that their food was in a condition that isn't ideal. And there also exist reversible thermochromic compounds. So these ones do not require regeneration. As they go above and below the set temperature, they change back and forth without issue. So they're used as cheap and quick temperature sensors. An example you might be familiar with is Coors Light. The mountains on their beverage cans turn blue when the temperature drops below 5 degrees Celsius. So that lets you, the consumer, know that your beverage is cold and ready to be consumed. So with the DSC Vesta, we can check out the reaction reversibility. Is it irreversible? Is it reversible? Can it be regenerated? As well as using the sample observation, we can actually look at the phase colors. So does it go from transparent to black, green to red? Next, we can look at the regeneration temperature or the transition temperatures. So when do all these reactions or phase changes occur at? So that you can tweak your formulation so that it occurs around your desired temperature range. So another type of compound that is big in food storage and cold chain is phase change materials. They're very important for thermal management. So let's take the simplest example, an ice pack. These are put in lunch boxes and coolers used to keep the content, the system, or your food cold. It works by using the phase change from ice to water to keep the temperature at a steady temperature. So for example, we take the CP of ice is around 2 kilojoules per kilogram Kelvin. So it's going to take 2 kilojoules to increase temperature by 1 degree Celsius up until it hits 0, where the phase change occurs. So at this point, we can see that it takes 334 kilojoules per kilogram, which is a much larger number than that in the specific heat capacity. So because of this, the temperature is going to be stalled or stopped at 0 until the entirety of the ice pack has melted, or 333 kilojoules worth. So we use this to keep our system or your food at 0. So in this case, you'll put in your lunch and it'll keep your lunch around this temperature while you bring it to work. So what makes a good PCM? What should you look out for? So first off, high specific heat capacity. This means that's going to take more temperature to increase, more energy to increase the temperature of your system, or in this case, your food. You look for a high enthalpy of fusion, same as before. Increasing the energy needed to melt the PCM will increase the time that it is spent at its transition temperature. Next, it needs to be melting in the desired range. So you could have the world's best PCM, but if the phase change is at 200 degrees Celsius, it's not going to be useful for food storage. And as Arya mentioned, you're going to need to know the thermal conductivity, because we want a high conductivity so that the PCM will absorb more heat from the food and there will be temperature equilibrium. And the first three, easily measured by DSC. We can get specific heat capacity, we can get the temperature of fusion, as well as the energy associated with it. And as previously mentioned, the K can be measured by Trident. There's actually one more very important criteria for a PCM, and that's food safe. We want this PCM to be food safe. It's going to be around food that's going to be consumed. So next, as you can see here on the right, a lot of these PCMs are, food safe. We have paraffin, wax, salt, fatty acid esters. So if I was going to use a PCM, what would I look for? For this example, I like using the lunchbox example. If I want to keep my lunch cool, let's see what I'd use. We see some of them melt at 10, 11, or even some of them melt over a large range because they're not a homogeneous sample. There are many things melting together. That might be a little bit too high for my liking. I might want to pick one that melts around 4, or maybe 3 or 0. Then next, we'll look at the latent heat of fusion, or the enthalpy. We want to pick one that has a large one because we want it to absorb as much heat as possible. And as you can see here, this one has a quite a bit larger number than the rest. So personally, I might want to go with this paraffin wax A6. Yeah, thank you so much for stopping by. Hopefully you learned something. And in addition to being a distributor of Rigaku, we also have a fully equipped lab, and we offer testing services. So if this could be helpful for you, if you're interested, just please reach out. And now I will be passing it along to my colleague, Arya Sharostambek, to speak a little bit about DMA in the cold chain.
Thank you so much, Alex and Arya, for your informative presentations. Hello, everyone. My name is Arya. I'm lab scientist at C-Therm Technologies. And today I'll be talking about the applications of dynamic mechanical analysis in cold chain storage materials. Here, I'm going to share my slides with you. Already. Okay, so again, today topic will be high performance dynamic mechanical analysis of cold chain storage material. C-Therm is partner with Metrovib, manufacturer of DMA instruments. Metrovib offers a variety of different DMA instruments, from desktop series to high performance DMA that are suitable for fatigue testing, high force and high frequency range of testing for DMA, and also a very high frequency product line called VHS for measuring viscoelastic properties of the material. Okay, so before we start talking about the applications of the DMA in cold chain storage materials, I would like to walk you through the principles of DMA, of how this method operates, and how we can measure properties that can be useful for your research and development. So DMA is the most accurate technique for measuring viscoelastic properties of the materials. And viscoelastic materials cover a huge range of different materials, from polymer to elastomers, with different applications. And this broad range is also very important in food packaging material and cold chain storage, from food packaging to pharmaceutical and other applications within that temperature. So basically, the way that DMA works, or better to say, a DMA instrument works, is that the DMA consists of applying a dynamic force excitation to a specimen of the material, measuring the applied force and the resulting deformation. So the nature of viscoelasticity of materials after each test shows a phase lag between the force or displacement applied on the sample and the response recorded. And this delay is called phase angle. And this is very important with viscoelastic properties, and it plays a key role here. So as you can see in this figure, you can see how a DMA works. So basically, this deformation mode is tension. So your specimen is mounted in the sample holder, and it's being deformed with a dynamic periodic load during time. And so MetroVip DMA is capable of reaching the temperatures low to minus 150 degrees C all the way up to 500 degrees C, which is a very broad range and definitely suitable for testing cold chain storage materials for different purposes. Okay, but what we can obtain from a DMA test. So there are many different parameters that it can benefit from a DMA test, but really the key parameters that is very useful for different applications. And there is various advantages with measuring those are modulus, which is basically the material's overall resistance to deformation, or in other words, the ratio of stress to strain. And this parameter has two components, viscous or loss modulus, which expresses the ability of material to dissipate energy through heat. And the other component is elastic or storage modulus, which expresses the ability of material to store that energy. And as you can see, these two different components can be very useful to express different behavior of a viscoelastic material. And we also have a very important parameters, which is called tan delta. This parameter is shown by the ratio of loss modulus or viscous modulus over storage modulus, and it's called tan delta. And this parameter is very important for measuring different applications and evaluating material for different applications. For example, the most famous one is glass transition temperature. So basically running a temperature sweep test on a specimen, as you can see, gives you a peak in tan delta, and that peak is used to determine the glass transition temperature. So this is very important to note that the glass transition temperature evaluation using a DMA technique is 100 times more accurate than any other techniques available. So it doesn't matter working with any other instrument, DMA gives you 100 times more accuracy measuring a glass transition temperature. And this is extremely important for cold chain storage materials, because basically what's happening to the material during transportation or different stages of the process is mechanical deformation. So measuring and recording that response from a mechanical deformation can give you the highest accuracy for your results. An important point to know is that testing samples at lower temperatures, especially viscoelastic materials, requires high force capability. Since the material goes lower in temperatures, it becomes stiffer, and more mechanical force is needed in order to deform the material and have an accurate measurement of viscoelastic properties. So in other words, the colder the temperature, the higher the stiffness, and the more brittle the material. For example, a useful case for measuring cold chain storage material at lower temperatures is like the cold snapping. That is very common for polypropylene for food packaging. And so this is the importance of testing material at lower temperatures. So just to wrap up this slide, don't forget, it's very important to test materials at lower temperature because it evaluates the brittleness of the material at different stages. However, in order to mechanically deform the samples, you need high force capabilities, and DMA Plus series of MetroVib instrument can definitely provide you that tools for your testing. So this is a temperature sweep test using dynamic mechanical analysis technique. And as you can see, glass transition temperature happens at alpha transition, the midpoint. And before that is exactly the point that material can be more prone to mechanical failures and becomes more brittle. But as you can see, there are different stages to that. So before glass transition temperature, we all know material is stiffer, but we don't know what's happening exactly at each different stages. DMA is the only technique available that gives you details about transitions, secondary transitions lower than glass transition temperature. For example, before glass transition temperatures, you can see 3 different stages of the material secondary transition. So the beta transition gives you information about the side group movement of a polymer chain. And the gamma gives you a bend and stretch of the polymer chains. And the delta gives you information about local motion. So this makes DMA extremely useful for applications at lower temperatures, since at different stages, the brittleness can be different and the behavior of the material can be different. And this is the importance of DMA. And in the region that you can see with the blue brace, this is the stiff range of the material. And it's exactly the region that you need to have an instrument that is capable of deforming the sample within the range of stiffness. So let's take a look at 2 case studies here. So this case used DOM, polyoxymethylene, which is a common polymer with applications for gearing or bearing. And so it's really famous for its mechanical strength. So you definitely need high capabilities to test this material accurately, especially for lower temperatures. So as you can see, running a temperature sweep test using a MetroVib DMA can give you the insight at different stages of the transition. So starting at minus 63, around that temperature point, you see the first transition happens -2, the second one and the third one 140 degrees C. So this test was done with the frequency of 5 hertz and the temperature of -70 to 160 degrees C and heating rate of 2 degrees C per minute. So another application is the glass transition temperature. As I mentioned before, DMA has the highest accuracy for measuring glass transition temperature across all the methods. And for many applications and cases for transportation and different processes for cold chain storage materials, we have different frequencies in the process. And that can come from different engines vibration and other sources. But it's important to understand the behavior of materials at different frequencies. And the reason behind that is that, as you can see, one of the most important transitions, which is glass transition temperature, can shift to the higher temperatures, having a higher frequency. And this is, again, the importance of having a DMA that gives you the access to different ranges of the frequency. This test was done on PMMA, another famous polymer material, for different applications. And this test used different frequencies from 1 hertz, 10 hertz to 50 hertz. And the temperature was from -60 to 100 degrees C with a heating rate of 2 degrees C per minute. So as I mentioned, with frequency of 1 hertz, you can see that the glass transition temperature happens at -21 degrees C. With increasing the frequency to 10 hertz, the glass transition temperature goes to lower temperature of -30 degrees C. And continuing increasing the frequency to 50 hertz, you can see that now the glass transition temperature happens at -39. This can be very important in evaluating that brittleness of the material at different frequencies, and it can prevent the failures at different stages. So the important lesson from this slide is that you need to have an instrument to measure viscoelastic property as your DMA, that the test stays consistent. You shouldn't have any interruption for different stiffness at different temperatures. The test should be consistent across the temperature. And for example, it shouldn't be recalibrated, or the sensor replacement can interrupt the test. But MetroVip DMA offers you this capability to measure the material property starting from very low temperatures like -150 with very high stiffness all the way up to 500 degrees C without interruption. Another important factor is frequency. As I mentioned, frequency can have a very important impact on the test results, and it's important to have a robust instrument that has a rigid test frame, that it doesn't get interrupted with higher frequency because of the compliance of the instrument, which is very common in DMA. And DMA plus series of MetroVip can reach the frequency up to 1,000 hertz and measure the data without any extrapolation or master curve calculation. So there's no any calculation happening between, and you can have the direct measurement from your material at higher frequencies, different temperatures. And as I mentioned, due to the rigid test frame of the instrument, you don't have any effect of compliance of the instrument itself. And it's very reliable instrument to test for different conditions. So speaking about DMA, MetroVip DMAs, all the tests that I showed in previous slides was done using a DMA plus 300 with higher capability, such as high frequency and high force. And I would like to really show you a MetroVip instrument series that is provided by the MetroVip. And so we have a low force DMA or desktop series, and they are suitable for any lab and for like a classic DMA test. They're excellent for measuring glass transition temperature. And really the approach here is just plug and play, and you can really have all the parameters that you need for your research in a lab scale using this series, desktop series DMA 25 and 25 and 50. DMA 25 is capable of applying 25 Newton force peak to peak and 50 Newton force peak to peak for DMA 50. And that takes us to DMA plus series with higher force capability and higher frequency capability. So a desktop series can go up to 200 hertz for frequency, but plus series DMA can go up to 1,000 hertz frequency and up to 2,000 Newton force peak to peak with added capability, for example, fatigue testing, heat built-up test, and an automated solution provided by MetroVip. And basically, you can run your test 24/7 without interruption using a robotic arm. And on the right-hand side, you can see a high-frequency analyzer, VHF 10.4, that can measure the viscoelastic properties of material for higher frequencies, ranging from 100 hertz to 10,000 hertz experimentally, without any calculations or any master curve building or extrapolation. And so here at C-Therm, we have a DMA Plus 300 available for your testing. And as my colleagues mentioned before, we have thermal analysis lab here, and it's a full thermal analysis lab with different instruments for measuring thermal conductivity. We have transient method. We have Trident instrument with different sensors, as Aria mentioned during the first section of the webinar. And we also have thermal analysis, TMA, DSC, and STA, and also DMA for measuring viscoelastic property. So if you are curious about testing your material, and if you need your data for your research, please feel free to contact us in the link in the caption, and we'll be more than happy to provide you technical consultation and help you with your research. So that brings us to the end of today's webinar. If you find this topic or any other topics interesting for you and related to thermal analysis, please feel free to go to our website, and we have a library of different webinars and different blog posts working with thermal analysis for different applications and different instruments, different methods. It's really a useful library to enhance your knowledge for thermal properties of the materials. If you're interested, you can follow us on LinkedIn and stay tuned for the upcoming webinars and new blog posts. Also, we have 2 upcoming webinars. One titled Evaluating Thermal Conductivity of Nanoparticles Enhanced Fluids, April 29th. And the other one is an inline quality assurance of sediment detection in 2K polymer adhesives with thermal property sensors in dispensing equipment, May 15th. Feel free to register for these 2 webinars. And also we'll be at Thermal Management Expo North America and Material Characterization Showcase. Please feel free, if you're there, stop by and have a chat with us. We'll be more than happy to help you. And this webinar is recorded, and link can be shared if you have any colleagues or friends that couldn't make it for today's webinar. And that will take us to the end of today's webinar. We are going to stop the webinar's recording here, and then we'll move on to the questions. And we'll be more than happy to answer all the questions.